Hello everyone, my name is Nivikit. You can also call me Avon, and I'm currently a research fellow at the Department of Electronic and Electrical Engineering, University College London. Right, and today I actually record this video because many people are still not yet familiar with fluid antenna system, and I believe some of the people have actually heard of this system, but do not know what this system actually is. Therefore, I would like to take this opportunity to explain what is fluid antenna system and also discuss the opportunities, challenges, and applications that are associated with fluid antenna system. And before I begin this very interesting talk, I would also like to thank my supervisor, Professor Kai Kit Wong. So he's also the inventor of fluid antenna system. I would like to thank my co-supervisor, Professor Kim Pai Tong, as well as the collaborators, Professor Rochmersh, Professor Chamberlain Cha, and Professor Cao Wang. Then I would also like to thank my research fellow colleagues, Dr. Hao Shi, Dr. Farshad Rostami, and Dr. Han Jiang Hong, as well as our very valuable PhD students, Noah, Bowie, and also Helvins. So all of them have actually been working very extensively on fluid antenna system. Therefore, to be honest with you, I wouldn't be able to make this presentation without their help. Therefore, I would really like to acknowledge them first. So the objective of this talk are three. First, I would like to introduce you to the fundamentals of fluid antenna system. And here I will discuss the definition of fluid antenna system. I'll give you some examples of fluid antennas by our definition. And then I'll also talk about how fluid antenna system started, how it works, and I will present the performance of fluid antenna system, as well as the parameters that can affect this performance. Next, I will discuss about the opportunities and challenges of fluid antenna system. In particular, what are some of the things that fluid antenna system can do differently as compared to traditional antenna system in channel estimation, MIMO, multiple access, or interference management and massive communication. Okay, then lastly, I would like to explore the applications of fluid antenna system with you. So for example, here I will discuss about how we can combine fluid antenna system and reconfigurable intelligent services (RRS), next generation multiple access (NGMA), non-terrestrial network (NTN), physical layer security (PLS), artificial intelligence (AI), wireless power transfer (WPT), and integrated sensing and communication (ISAC). So first, let us talk about the fundamentals of fluid antenna system, right? And let us begin with this question. What is fluid antenna system or FAS? So by just looking at this terminology, you might guess that this is a wireless communication system that employs antenna that are made of liquid or gas, right? Because this is the definition of fluid, right? But is this true? Well, this is not entirely true. To understand what FAS is, we actually have to look at the early papers as well as the formal definition. And the definition is FAS actually represents any software controllable fluidic, conductive, or dielectric element that can alter their shape and position to reconfigure the gain, radiation pattern, operating frequency, and other characteristics. So what this means is that FAS may not be employing antenna that just made out of liquid or gas. It can be others. It actually consider a wide range of antennas, and this may include, but not limited to, liquid-based antennas, pixel-based antennas, and meta-designed antenna. So for your information, these are some of the prototypes that our professors and the collaborators have developed. So here I'll explain a little bit about what are these antennas, all right? So in liquid-based antenna, it actually uses liquid metal, where this liquid metal is encapsulated in a container. And in this container, there are actually pumps. So this pump can alter the position of the liquid metal. And as the position changes from one location to another location, the channel gain of the transceiver would also change, right? So this is how it works. Now, in pixel-based antenna, we have multiple modes, and as this mode changes, the connection between these pixels also changes. And these changes are made to mimic as if there's a radiating element within a given space and it can move within this given space. All right. So what about meta design antenna? In meta design antennas, there are multiple ports, and this port can actually be activated or deactivated, right? And when it is activated, it is radiating. Otherwise, it is not. Okay, so these are some of the antennas. So FAS was first introduced in 2020 by Professor Kidd. And since then, it has actually inspired many recent related research studies. For example, movable antenna system, flexible position MIMO system, reconfigurable antenna MIMO system, flexible antenna arrays, and many more. So how did FAST started, right? So I'm very lucky because I work under Professor Kidd. Therefore, I actually had the opportunity to ask him this question. And he explained to us that FAST actually comes from this Bruce Lee philosophy. Okay, so this is his inspiration, his motivation. So who is Bruce Lee? Bruce Lee is actually an actor and he's also a martial artist. In particular, he's the founder of Jeet Kune Do. Right, and as I mentioned, he's a celebrity. Therefore, he was actually being interviewed in a Pierre Berton show, which was aired in September 1971. So in this show, he actually gave a very famous quote. And this is what he said. He said, empty your mind, be formless, shapeless, like water. If you put water into a cup, it becomes the cup. You put water in a bottle, it becomes the bottle. You put it in a teapot, it becomes the teapot. Now, water can flow or it can crash. Be water, my friend. So there's a quote that he actually gave in the show to express his understanding in martial art, to explain why he can attack and defend effectively. Right? But this philosophy is related to martial art. Therefore, I believe you might ask, how is this related to wireless communication system then? Right? Now, let us look at our existing wireless communication system. Then you realize that we have actually been employing traditional antenna with fixed configuration. For example, the position is fixed, the shape is fixed, and so forth. As a result, we can refer this as the traditional antenna system class, right? And what this analogously means is that such system cannot actually flow or crash like water. Thus, Professor Kidd actually think that we can apply this philosophy, this Bruce Lee philosophy to wireless communication. Okay, in particular, we can actually ask, can our antenna be formless, shapeless like fluid, and adjusted to different situations in wireless communication? And of course, the answer to this is yes, and this has actually inspired the fluid antenna with flexible configuration. All right, so the term fluid in FAST is sort of like a metaphor. It is used to highlight the dynamic nature of the antennas and the motivation behind this idea. Okay, so just like Bruce Lee said in martial art, be water, my friend. What Kid would like to express in wireless communication is be fluid, my antenna. So how does FAST work? Well, to understand in the simplest way, we can imagine that we have a traditional antenna transmitter where the position of the antenna is fixed, as shown in this figure here. Right? Now, let us further imagine that we have a liquid-based antenna receiver, as shown in this figure here. And in this receiver, there's a length of W lambda, where lambda here is the wavelength of the carrier frequency. And within this length, there are actually n preset locations, which are also known as ports. So these ports are actually the location where the antenna can be relocated at. And note that this is not just limited to liquid-based antenna receiver. It can also apply to any other receiver. For example, it can apply to meta design antenna. For example, in meta design antenna, we have multiple ports, and one of the ports can be active, and therefore the active port is radiating, right? So they are analogous. Now, as you can see, W and N here are actually the system parameters. So imagine that in wireless communication system, you actually have such receiver. Then what can the receiver do? So the receiver can then reconfigure the antenna properties, right? For example, it can move the liquid metal from one port to another port, or the active ports can be switched from one to another. And as the liquid metal or the active port changes its position, the channel gain will also change as shown in this figure here, right? So in certain location or in certain ports, the receiver might actually experience deep fading. And in certain location, it might actually experience very strong channel gain. So as illustrated in this example, one of the key principles of FAS is that FAS aims to fully exploit the spatial diversity within a given space. Now, just as a side note, FAS is also related to holographic MIMO system in some contexts. For example, the key idea of holographic MIMO system is to use the entire space, the entire continuous aperture for transmission. In FAST, we similarly use the entire given space, but we only use certain locations for transmission. So in some sense, we can say that fluid antenna system is sort of like a holographic MIMO system with antenna selection, where certain positions are used for transmission. Okay, so that is how FAST and holographic MIMO system are sort of like correlated in some context. So in this example, all right, I've talked about a 1D movement, a one-dimensional movement thing, but this principle can be easily extended to a more advanced one, right? For example, it can be extended to two-dimensional or three-dimensional movement. And we can further imagine that the orientations of the antenna can actually be rotated. Furthermore, the platform of the antenna may not be rigid, it can be flexibly shaped as well. So as time progresses, the principle of FAST is also going to evolve. And I believe that this is also the essence of research, right? So next, let us look at the performance of FAST. Okay, so what are the benefits of FAST? Why do we want to employ FAST? So one of the benefits of FAST is outage probability. Okay, so outage probability is the likelihood that the rate is below a certain threshold. So for example, if the outage probability is 1, then it means that the rate is always below that threshold, right? In contrast, if the outage probability is very low, then the rate is usually above that threshold. So a lower outage probability is generally preferred. Okay, now, as I mentioned just now, W is a system parameter. So if W is sufficiently large, then the outage probability of FAST can actually be significantly reduced as N increases, where N is also a system parameter. So for example, as shown in this figure here, all right, let us focus where the SNR is 35 dB. You can see that when N is equals to 2, the outage probability is 10 to the power of -1. Now, if we increase the ports from N equals to 2 to N equals to 10, you can see that the outage probability actually decreases to 10 to the power of -5. So these actually use a 10 to the power of 4 gain, right, which is very substantial. In other words, FAST can actually offer a very reliable communication. Okay, as a result, you may want to use it. Now, if you are interested in outage probability or the diversity gain, you can also refer to this paper here. So this paper actually carried out a very comprehensive analysis on the outage probability and diversity gain. Sorry. So another benefit of FAST is the power consumption. Okay, so here the definition of power consumption is the amount of power consumed by the transmitter to ensure a specific rate. So if FAS is employed, then it actually requires less transmit power to achieve a specific rate as compared to traditional antenna system tasks. For instance, as shown in this figure here, if traditional antenna system is employed, in particular the single input and single output system, you can see that we actually need 48 dBm or near the 48 dBm to achieve a specific rate. But if we employ fluid antenna either at the transmitter or the receiver side, you can see that the power consumption actually reduced by 8 dB. And if you employ fluid antenna at both sides, then this can actually yield an additional 4 dB gain, so a total of 12 dB gain. So this power saving is actually very substantial, and it can save a lot of money for the operators, right? So these are some of the benefits of FAS, and if you'd like to know more about the benefit of FAS as well as the rationale behind this performance improvement, you can also look at this tutorial paper here. But don't worry, as we progress, we are also going to talk more about the benefits of FAS, right? So from the previous result, we can see that the performance of FAS mainly depends on the system parameter, such as the length, W lambda, and also the ports N, right? So to understand why, we can actually look at this figure here. This figure shows the amplitude versus the length, and you can see that as W increases, the amplitude or the channel gain actually have more peaks and valleys, right? So what this intuitively means is that as W increases, it actually introduces more spatial diversity gain, all right? So this is actually a good thing, but it's a case where N approaches infinity, right? In practice, N is usually finite, but it can be very large. For example, it can be 101, 201, or 1001, right? Then in that case, it will resemble a FAS because this system is able to access all of the peaks and valleys. So you might have a question, does this mean that the bigger N, the better the system is? Well, not necessarily, I would say. It depends on the size. So for example, if N is sufficiently large, in this case, when N equals to 101, then increasing the number of ports will not actually use a lot of gain. Why? Because when N equals to 101, you can see that the system is able to access most of the peaks and valleys already. As a result, increasing N will not yield a significant performance gain here, right? Nevertheless, if N is small, this could actually affect the performance significantly. For example, when W is 4 and N equals to 9, you can see that we actually have ports that are separated by half a wavelength, right? So what this resembles is that this resembles a traditional antenna system with antenna selection, okay? Tasked with antenna selection, where the antennas are separated by half a wavelength. And you can see in this example, there would be a problem. That is, this system would actually face outage because all of these ports are unable to satisfy this minimum amplitude. All right, as a result, outage can occur. So this is how a small N could affect the performance, right? So to a certain extent, you can say that the limitation of FAS is that it depends on the system parameter. But the good news is that the system parameter can be optimized. In other words, the antenna can be well designed, and that can actually ensure a good quality or good performance of the fluid antenna system.